Hello guys, this is Carter, and in today's video I want to go over the second fundamental theorem in functions that are defined by an integral. So as we know, the fundamental theorem of calculus allows us to use the derivative of a function to calculate the change of that function, and we can rewrite the fundamental theorem as f of b equals f of a plus the integral of f prime of x from a to b dx. And what we see here is that the endpoint of a function is equal to the starting point of a function plus the integral of f prime of x from a to b, which is essentially the accumulation of the rate of change of the function, because we know that this integral is accumulating all of these little tiny Riemann sums of f prime of x, or the rate of change. And this accumulation of the rate of change from a to b is what causes the function to move from its starting point of a to its endpoint of b. So let's kind of see what this means. So with this graph of f prime of x, this is the function's rate of change at any time. And as we can see by this yellow region, we are taking the integral of f prime of x from a to b. We are finding the area under the curve. And by taking the integral, we are essentially accumulating the rate of change by adding up all of these tiny Riemann sums, just like this, which we learned about last unit, what Riemann sums are. And all these tiny Riemann sums, this can tell us how much a function is changing by over time. This is essential because while in basic algebra, we always had functions with constant slopes, like y equals 2x plus 5, where it's a constant slope. But now we're seeing these functions with anything but a constant slope. The slope is positive here, negative here. We just can't use y equals MX+B anymore, obviously. So what we do is we take the integral of the rate of change, and this is the accumulation of the rate of change, and we can use this to figure out what the function's y value is at a certain moment in time when the slope is varying a lot. Okay, so what if we want to be able to see graphically how much the accumulation of the rate of change is affecting the function? And this is basically like saying y equals mx plus b. How much is the slope of, y, let's say we have y equals 2x plus 5. How much is the slope of 2 affecting the function's position and how it's changing over time? Well, that's the same thing here. How are we going to see graphically how the accumulation of the rate of change is affecting the function? Well, what we do is we can have a function defined by an integral, which we haven't seen yet. Before, we've been taking integrals like this, where there's numbers in the upper and lower bounds of 2x or whatever, any function. But now we are going to put a variable in the upper bound, and this is a segue into the second fundamental theorem. So the second fundamental theorem says that f of x equals the integral of g of t from a to x dt. And you guys are probably really confused, like why is there a t and an x? What does this all mean? What's going on? Well, let's just think about this. So what are we doing here? Well, by putting x in the upper bound, we can graph the accumulation of the rate of change of f, which essentially is telling us how the function is being affected by the rate of change at a particular moment in time. What if we find the derivative of f? Well, f of x we see is just g of x. And why is this true? Well, what we do when we have an integral, let's just work through this. We find the antiderivative of a function, which is we are representing as uppercase g of t, and then we plug in the bounds. So uppercase g of x minus uppercase g of a equals f of x. And then if we want to find the derivative of that, the derivative of g of x is just lowercase g of x minus uppercase g of a. Well, that's just going to be a number. So the derivative of a number is just 0. So it's just plus 0. So that is why we know this to be true. And this is very important. And what we will see is that to find the derivative of a function defined by an integral, we will simply just plug the upper bound into this quote-unquote dummy variable. So yeah, let me explain why we're using a t here. Well, the reason we are using this t, it's a dummy variable, and it's good that we use t rather than x because x is representing the end of the interval over which we are finding the area. So it doesn't really make sense for us to use x to represent an arbitrary point inside the interval. So that is why we use t here, but we end up plugging x in when we take the derivative. So that is why we can say f prime of x is just g of x, because we are simply plugging in x here. So let's think about this a little more. Let's say, for example, we have f of x equals the integral from 0 to x of 2t dt. Well, if we want to kind of see what this integral means, we take the antiderivative of 2t, which is t squared, and then we plug in the bounds, x and 0, which comes out to x squared minus 0 squared, so just x squared. So as we can see here, if we're graphing a function with an integral from 0 to x, what that is doing is just graphing the antiderivative of the function that is here, because the antiderivative of 2x is just x squared. So my comment here is essentially a function defined by an integral with bounds of 0 and x is just the antiderivative of the function inside of the integral. That is true. And we can see this here. If we graph 2t, it is this, line with a slope of 2, intersects the x-axis. And if we graph this integral of 2t from 0 to x, that is the antiderivative of this function, 2t. Okay, so what if we want to find the derivative of a function defined by an integral? So if we want to find this function's derivative, all we do, as I said a few slides ago, is that you just plug in the upper bound into here. So why does this work? And why can we just ignore this lower bound? What about this 0 here? Why can we just ignore it? Doesn't that have some implications? Well, what we will see, let's just take this integral, which we already did earlier. We just get the antiderivative of 2x, or 2t, which is t squared, and then we plug in 0 and x, we get x squared minus 0 squared. And when we find the derivative of x squared minus 0 squared doesn't have a derivative because it's just a number. And we can see this with any lower bound. It doesn't just have to be 0. So here I did a lower bound of -1. And what we can see here, when we take the antiderivative of this function, function inside of the integral, what we can see here is that we get t squared, and if we plug in x and -1, we get x squared minus 1. And when we take the derivative of that, the minus 1 is irrelevant because the derivative of a number is 0, so it doesn't matter. So what we can see by the graph of these two integrals, they are exactly the same, except the blue graph has a lower bound of 0 and the red graph has a lower bound of -1. This represents their original function. So as we can see, there is a translation from the blue graph to the red graph of -1 because of this lower bound. But the derivative of both functions will be exactly the same because the slope of these graphs at every point will be exactly the same because this translation is not affecting the slope. So my comment is, while changing the lower bound of a function defined by an integral could translate the function, as we can see here, it will not change the derivative of the function because the derivative of a number is 0. Okay, now I want to explain how the chain rule applies when we take the derivative of functions defined by an integral. So what we know is that when we take the derivative of this function with an integral in it, let's just say the integral of g of t from a to h of x, we are just plugging in this upper bound we are substituting that out for t, essentially. So we get g, and we plug in h of x, so g of h of x. But we need to multiply by h prime of x. Here's why. Let me explain it here. If we have f of x equals the integral of 2t from 0 to x squared dt, then this is just going to, if we find the antiderivative of 2t, which is t squared, and then we plug in values, it's going to come out to x squared squared plus 0 squared. And so this is our function once we take the integral. This, when we find the derivative, we're going to do 2 times x squared to the first power, but we have to watch out for the chain rule. It has chain rule implications. We have to multiply the inside, we have to multiply that by its own derivative, so 2x. So this would be 2x squared times 2x. The common error here is when students see this function like this, where it's just the integral of 2t from 0 to x squared dt. So they'll be like, oh, I'll just plug in x squared for t, and it's just going to be, the derivative will just be 2x squared. Well, that's not true, because we have to watch out for the chain rule. So in my previous slide, when I explained that all you have to do is plug in this upper bound and then multiply by the derivative of the upper bound, which we did here. We are plugging in this upper bound, so 2x squared, but we have to multiply by its derivative, which is 2x. Oh, I left my notes. That is unfortunate. Oh, okay, here we go. All right. So lastly, I just want to go over functions that are defined by integrals where both the upper bound and lower bound have variables in them. We can't just plug in the upper bound when taking the derivative of these kind of functions, because, like, for instance here, f of x equals the integral of 2t from x to 2x. We can't just disregard this x, because this x is going to have its own derivative, as we see when we take the integral of this. When we take the antiderivative of 2t, we get t squared, and we plug in x and 2x, and we get 2x squared minus x squared. Both of these we can take the derivative of. So it's going to come out to be, after doing some derivatives, it's going to come out to be 6x. So the common error here would be just simply plugging in 2x and disregarding this x and getting 4x and being like, okay, that's our derivative. Well, no, that's not true. We have to account for x. And also, I just made an error myself. It wouldn't be 4x because we would have to multiply by 2, the chain rule implications. This is what the stupid mistake would be if someone was like, forgot to plug in the lower bound, because the lower bound is a variable, so we have to account for it. If someone just forgot and they just were like, okay, f of x equals the integral of 2t, that equals, you know, the f prime, oh, well, I can just plug in 2x in for t, and I'll just do 2 times 2x, and then we got to do the chain rule, right? And they'll be like, okay, that's the answer. Well, no, that's not the answer. We have to account for this x, because when we plug in the x, when we take this integral, that is going to have its own derivative, which we will see is negative 2x. So this is going to come out to be 6x. So that's all I'm going to go over today. I'm going to make a part 2 to this video where I'm going to go over the application of this and how we can look at these graphs and really what they're going to test on the FRQs and AP Calculus. But thank you guys for watching.